Hello, my name is Riley Brown, and I will be discussing joint work with Prahlad Kasurirangan, Joe Mitchell, and Valentin Polishuk regarding the minimum convex cover problem and hidden set problem in simple polygons. The problems we have today, we have an example of a packing problem and an example of a covering problem. A packing problem generally is a problem which poses how many objects can we possibly fit inside a particular domain. So a good example of this is from the graph theory domain is the independent set number. The independent set problem rather poses how many vertices can we pack into this graph where no two of them share an edge. So if we look at this vertex here and this vertex here, there's no edge between any one in the set, or any two in the set, I should say. So since there's no edge here, we know that there's an independent set of size 2. A covering problem on the other side asks what's the fewest number of objects that we need to cover a whole domain. So a good example of this is the clique cover problem, where we want to use cliques. Those are sort of subsets of vertices where they're all neighbors with each other. So we want to find the minimum number of these that we need to cover every vertex. So if we add this pair here, we have every single vertex is part of some clique inside of here. So it's a clique cover of size 2. The nice fact is that the independent set number is always less than or equal to the clique cover number. So this size of this independent set is always, which is 2, is always less than or equal to the size of the clique cover, which in this case is also 2. So they're equal in this particular instance. For our packing problem, and it's sort of our analog of independent set, we have hidden set, which is a geometric problem where we want to place as many points in here so that no two of them see each other, and sort of we can give an intuitive idea of what this is by first placing this point. And as you can see, these 2 points don't really see each other if we think in sort of the standard way, and then we place this other one. And what is the standard way? The standard way is that if you look at the line segments between them, it passes outside of the polygon. And this intuitively is like if you're standing in a room, this polygon is the walls of a room. These guys would not be able to see each other because there'd be a wall in the way. So no matter how they turn, they can't look at each other. So in terms of the number of these maximum number of hidden points, we call this HS of P, or the hidden set number of the polygon. Finding this hidden set number is known to be NP-hard. So that's known since as far back as 1989. This is NP-hard to determine what this maximum number of hidden points that we possibly could need. The APX hardness, that came around in 2002. So even to approximate these within some constant factor, it's NP-hard. There exists some epsilon where we can't approximate it better than that. So a constant factor, if we can get some constant factor, that would be the best we could do. And then from there, it's just a matter of whittling that constant down until we've hit the boundary with where it's NP-hard to do so. And so far, there has been no approximation algorithm, no log approx, no log squared. There's been no approximation algorithm whatsoever for trying to find the maximum hidden set within a polygon. Until now. We present a 1/8 approximation. So in terms of the maximum, our result will always be at least 1/8 of the size. For convex cover, we have this covering problem where instead of cliques, in our case, we're looking at convex pieces. So those are regions of the polygon where everybody sees each other. So intuitively, you can look at the angles in this, and they're all less than 180. We call it a convex polygon. So this piece of the polygon is convex because everybody sees each other. And we want to find the minimum number of these pieces that we need to overlay on top of each other so that we've covered the whole thing. And note how we can choose any subpolygon. So it doesn't need to be restricted to the vertices in terms of the boundary. It could be any subsection, and we're allowing to overlap. So this green and this blue, they overlap a lot. So because of this overlap allowance, we're able to just define this convex cover problem, where we're trying to cover everything with the fewest number of convex pieces. We'll call that number the convex cover number of the polygon. So for the current computational results, we also know that this problem is APX hard. And we've known since 2003. So both of these problems are pretty much, in terms of the APX hardness, about as old as I am. And in terms of the first constant factor results for both, we present them. So in terms of we have additional hardness result from Mikhail Abramson in 2021, from FOCS 2021, that it proves that it's as hard as the existential theory of the reals. But in terms of the approximation, that's been known since 2003, APX hard. And in terms of the positive results, we do have an approximation algorithm for convex cover. However, it's a log approx. And this log approx has a factor in the O, in sort of the constant factor, has an additional 16 behind it, which, I mean, is not terribly large, especially when we look at the runtime is n to the 29 log n. We were able to bring both of those down, both the actual, not just the factor we bring from log n to constant, but we also bring that constant in front to down to a 6. We have a 6 approximation. So on all values of n, our algorithm will run faster, and it will run, it'll produce less pieces. So we've managed to make a pretty good improvement on the current work. And our algorithm runs in nearly quadratic time, so it's a little bit more feasible for implementation. The sort of difficulty of the convex cover problem and why it's been very hard to develop results for it in the last 20 years is that the problem can't really be sectioned off. So if we look at this this polygon here, if we wanted to separate it into a bunch of convex pieces where there's no overlap, this is actually polynomial. It can be solved in around cubic time. So the partitioning, this allows us to do it in polynomial time, whereas with our problem in terms of the cover, because of the overlap, it's heavily used in the hardness proof to develop the result. Because of that overlap, it actually becomes much more difficult to sort of section it off and use some kind of DP algorithm. So that's sort of the intuitive reason as to why this problem is so difficult and has been very long-standing in terms of developing a very effective approximation result. For the our discussion today, we're going to be relating the problems. And the interesting fact of hidden set and convex cover, and this was also discovered by Schirmer in 1989, was that the hidden set number is always less than or equal to the convex cover number. So this convex cover number is an upper bound on the hidden set number, and the hidden set number is always a lower bound on the convex cover number. And the intuitive reason behind this is because if we look at any particular convex piece, we can fit at most one hidden point inside of it. And that's because if we tried to fit 2 in, it would violate the definition of convex, because the whole point is that everybody in a convex piece sees each other. So if there was 2 hidden points, those points would be a violation of that definition. So we place this extra point, 1 for every convex piece, and we get that this hidden set number and this convex cover number actually happen to coincide. They're both 3. So there's a lower bound, upper bound relationship. And we can exploit that relationship to develop our algorithm. So the first thing we're going to do is we're going to break down into a simpler case. We're going to give a 2 approximation for a specific type of polygon, which we call weakly visible polygons. And this will translate into a 6 approximation for general polygons, because we can split general simple polygons into sort of 3, we can do a partition that will allow us to show that there's only an additional 3 factor lost when we respect the boundaries of that partition, and those pieces in the partition are weakly visible polygons. On the hidden set side, we have a 1/2 approximation for the weakly visible case, and then we have a 1/8 approximation for general simple polygons. So that's sort of the overview of the results. And obviously the 1/2 and the 1/8 are referring to the fact that it's a maximum problem for a hidden set, and the 2 and the 6 are referring to the fact that it is a minimization problem for the convex cover case. For simple polygons, for a simpler version of the problem, we're going to look at the weakly visible case, and there's a specific subclass of polygons where if we look at every single point inside of here, there's some line of sight where we can sort of touch down on the base. So as you can see, we're going around to all the vertices in this case. Every single vertex has a point along this red edge where we can touch down and see it. And there's a small restriction on this edge. It has to be the angles on either side of this have to be convex. If they were reflex, then our algorithm doesn't work. We use the properties here, but actually you could lose only a 2 factor, an additional 2 factor, if you wanted to deal with that specific case where they jutted down. But we're just going to be dealing with convex edges, so edges where both of these vertices are convex. And the reason we do that is because these weakly visible polygons with the convex edge have this thing called the chord property. The chord property states that if 2 points along the boundary, if they see each other, that means that there was no piece of the boundary here which came in and blocked it. So as you can see here, it was blocked by this green section of the boundary. And what's different between this and a normal polygon? Well, a normal polygon, you could have either side of this come in and sort of invade the space, cause the blocking. But with the weakly visible case, we know it's specifically the chain, the sort of subset of the vertices, that is the opposite side with our weakly visible edge, the edge that sees everything. So what we can use this chord property for, where this chord property is, if P does not see Q, then we know that it intersects this part in between. What we can use it for is to define a DAG on the edges of the polygon. So this is our weakly visible edge in purple. If we look at one of the other edges, other than the base edge, then we have that in blue here, if we have an E sub I that comes before an E sub j, and all the points in E sub I see all the points in E sub j, we can draw an arc between them in this DAG. And then what we'll do is we can draw, if we take all the points in E sub j, and then all the points in E sub k, they all see each other. Draw an arc between them. A nice property is that if E sees EJ and EJ sees EK, then EI sees EK. So there's a transitive property of these arcs. So, and it's specifically going in order. So if this has to come before this, and then this has to come before this, then these arc this way. So we have this triplet. So, and that allows us to define a DAG where there's this transitive property. And when that DAG has this transitive property, we can do some things for both of our problems. For a hidden set, we're going to start by finding an anti-chain of the edges in the graph. And that's a set of edges in this polygon where no 2 of the edges strongly see each other. So once again, strongly seeing meaning that all of the points in here, there must be some break from seeing, they can't possibly all see all the points in here. So as you can see, we have this blue dotted line indicating that some of the points over here don't see at least some of the points in here. And so that's what this set of edges is an anti-chain in that DAG, because they're sort of incomparable. None of these share arcs with each other. And that can be found in nearly quadratic time. It's due to a maximum flow result, where it was nearly linear maximum flow, and sort of nearly linear in the number of edges. In terms of the number of arcs we can possibly have n squared. So nearly n squared runtime. Then for our second step, what we're going to do is we're going to truncate these independent edges. And that's so that we no longer have the principle where there's this, okay, maybe some of them see each other. We want none of them to see none. So we want these to be kind of hidden sub edges. So we're going to truncate them down so that that is the case. And this truncating algorithm is going to take quadratic time, and it's going to yield us something where we can get a hidden set from it. So what we're going to start with is we're going to look at the last edge, and we're going to look at the first edge, and we're going to recurse down and break it into smaller subproblems using this first edge and this last edge. So we're going to have two cases that prop up. The first case is that the first edge sort of projects downwards onto this last edge. And what that means in this case is that so all of the points in here will see everything from here on down. So we're going to truncate the edge up to here. And actually now none of these will see none of these. And we're just looking at the interiors because we're only going to place our hidden points in the interior. So, and this is the case when we have this shortest path between the close vertices, so vi plus 1 and vj. The close vertices have a shortest path of link with one link in it. So we just have one segment. These guys directly see each other. Then we can do this truncation by the projecting onto each other. Then, once we truncate it, we will pair this edge which sees into here with the rest of the edges in our polygon. Our second case is when this shortest path has more than one jump inside of it. If that's the case, we'll take any of the vertices along our shortest path, and what we'll do is we'll take this line segment and we'll find the parallel line that goes through U, this vertex, along the path, and we'll truncate both of these using that parallel line. And what that'll mean is that all of these, none of these on the interior, we'll see none of these on the interior. And what we'll do is now, instead of splitting into giving just one subcase, we'll have the two subproblems pair all of this within here, since none of this can see into any of the edges in here. And then we'll pair all the edges in here in this subchain to here. So what we'll have is we've split into two subproblems in the second case. And either way, we've split it into we've split the problem further, and so that recursive we can write a recurrence, and the solution will be that it runs in around, at worst, quadratic time. And that's kind of, this one case where you're kind of just getting rid of one edge at a time, and in terms of calculating this truncation, it can take at worst O of n to find this shortest path. So we're gonna, once we've truncated the edges like this, it's very simple. Since none of the interiors see any of each other, we can simply just take the midpoints of the truncated edges, and that takes a linear amount of time. So the overall runtime is quadratic, and we get a hidden set, which is the same size as that sort of independent set of edges, or the anti-chain of edges. For convex cover, what we're going to do is we're going to find a path cover. And so a path cover of the DAG is a set of paths in the DAG where every one of the elements of the DAG are covered. So in this case, we have these arcs. This arc goes from here to here, and this arc goes from here to here, and this arc goes from here to here. And because of that transitive property, we know that all of these points see all of these points, and all of these points see all of these points, and so they form one giant convex piece together. For each of these paths, each path is a convex piece. And that also takes nearly quadratic time to find that path cover and find this first set of pieces. And note how they don't cover the entire polygon, but they cover all the edges. So first step in terms of covering everything and not just the edges, we want to extend these path pieces, and we're going to add a blue triangle to them. And this blue triangle is defined by taking this last vertex and finding the leftmost point along this base, which is the weakly visible base. And we're going to find the rightmost point for this first vertex, and they're going to come to an intersection point right around here, and that intersection point defines a blue triangle that we can extend. So we're not going to add any more pieces with this, we're just extending our current piece to include this blue triangle, and this takes quadratic time if we do it naively, just finding these points for each of them. Now we're going to add another point, another piece. So this piece is not combined with this, but they're sort of paired together in terms of we can amortize our number of pieces by saying that this additional triangle piece is one for every one of our paths. So this green triangle instead looks at the last vertex and finds the leftmost that it sees and the rightmost it sees. And so together, this forms like a green triangle, which we'll see some section of the base here. This also takes quadratic time. And so in our paper we give the full details, but the sort of the proof that why this gives all the coverage breaks into 3 cases, and in all 3 of the cases we're either covered by the blue triangle or we're covered by the green triangle. Obviously we're also covered, we're not including the case where it's covered by the red. So assuming that there was a point which was not covered by the red, it must be covered by the blue or the green. And there's 3 cases here. And when we add all of our blues to extend, and we add all of our greens as additional pieces, we'll have a full convex cover of the polygon. So what we're going to do to prove that these are related to each other is using a thing called Dilworth's theorem. And what that has to relate to is that the maximum anti-chain is actually the same size as the minimum path cover. So if we have a minimum anti-chain of size k, our hidden set was the same size, so that's less than or equal to the actual hidden set number, less than or equal to our convex cover number, which is, for our convex cover, we're using B. That convex cover we have at most 2 times as many pieces as we had the paths. So we have that 2k is that bound on the number of convex pieces. So what we have is we have a 2 approximation for convex cover, and we have a 1/2 approximation for the hidden set within this weakly visible polygon case. So yeah, we have this nearly quadratic time runtime for our convex cover, and the same for hidden set, but we can actually improve the runtime to deterministically n squared by producing a set of candidate points. So we give a little bit more detail in the paper, but basically we're able to find all truncations, like all the possible truncations of the edges, and place candidate points, one that's arbitrarily close to this side, one that's arbitrarily close to this side. So if we truncate, we either truncate this way or we truncate this way. And what we can do then is we can place our candidate points here and then use an existing result on the version of this problem where it's restricted to vertices. And that is a DP algorithm which runs in quadratic time. And that winds up being the bottleneck for that approach. And so we can get exactly quadratic time for hidden set. Now we look at the general case, and what we're going to do is we're going to break the general case into the weakly visible case. We're going to do that using a link distance map. So if we start at some convex vertex specifically, we're going to illuminate all the things that it sees. So this blue region is all the things that convex vertex sees. And we're going to have a little frontier, we call it a window, hence why this is also sometimes called a window partition. We're going to have this window where we can look at all the things that are the next link distance away. So all the things that see this blue window form this orange polygon. And now we have 3 fronts. And we just keep advancing the front until we've covered, or at least partitioned, I should say, until we've partitioned the entire polygon. This actually gives us a set of weakly visible polygons. As you can see, all of this orange region can be seen from this blue window. A nice property of this link distance map or window partition is that no convex body can cross more than 3 of the cells. So if we look at these example cells, the worst that we could possibly get is that we see some child, parent, child, or I guess sort of the sibling of these. We can have a convex body which goes to 2 of them, but we can't possibly have more than this triple situation, and that's because of the definition of our link distance is that if we could try to get 4, then intuitively we would be crossing into something which they don't really see each other. So they shouldn't see each other, or else the link distance would be lower. So we have this proof that no more than 3 cells can be crossed by any particular convex body. And what that implies for us is that if we respect the boundaries of the partition, we lose a factor of 3. So since we only lose a factor of 3, it yields a 6 approximation, because 3 times 6 approximation. In contrast, for the hidden set, we have instead we're going to have a factor of 4. So we're going to use this result that was developed by Allegria et al. In the EuroCG paper from 2019, where they were able to split the window partition into 4 visually independent classes of weakly visible polygons. So if you look at the blue class here, those are the class of polygons where their window was what we would call a right window, meaning that they made a right turn. So the origin is kind of both left and right. But if we look at these blue, if you look at the window where they came from, it's a right turn. So what happens is they're sort of the weakly visible polygons that sort of set at a depth of odd, that's an odd number. So in this case, we have link distance 1, link distance 2, link distance 3, link distance 3. So they're link distance odd, and odd link distance, and then they're from that right turn. So that forms the blue class, and then through other combinations of those 2 things like left and even and so on, we get our 4 classes. But the nice thing is that they're visually independent, so that means that any point in here cannot see any point in here, and any point in here cannot see any points in here. So they're independent from each other in terms of their visibility. And what this implies for us is that if we take the hidden set from any of these, if we take the hidden set from this blue, this blue, this blue, they're hidden from each other. So what we can do is we can take the best of those 4 classes, 1/4 times 1/2, a 1/8 approximation. We've lost at most 7/8 of the points when we take this best of the 4. So it can't be any worse. It can be better. It can't be any worse than 1/8. So in terms of the combinatorial bounds, what this says for us is that actually the convex cover number is always less than or equal to 8 times the hidden set number, and that comes down from here. If we look at the convex pieces in each of these weakly visible sets, at most 2 times as many convex pieces. So if we have 1/8 approximation, we have at most 8 times as many convex pieces as hidden points. For the convex cover number in weakly visible, we have that 2 gap, and that comes directly from our algorithm. So we also have some other results. So for like star-shaped polygons and things, most of them sit in between this 8 and this 2 factor. And we give a little bit more of the details in the full version of this paper, but the idea is that we actually are able to develop combinatorial bounds, and this settles a conjecture that I and a colleague of mine had in 2021 regarding these problems, and that was that there was a constant in the difference for simple polygons. So in conclusion, we have a 6 approximation for convex cover and a 1/8 approximation for hidden set. and those are both in nearly quadratic or quadratic time. So what we have is somewhat feasible for implementation algorithms, which have these provable guarantees that their factors are at worst a constant. And these are the first constant factor approximation algorithms for these long-standing, as older than I am, problems. And honestly, probably far older than a lot of people with respect to some of the early work with convex cover. But for in terms of hardness approximation, about as old as I am, we finally have an answer. It's APX complete for both of these problems. So some open problems. Can we get a better runtime for convex cover? So the current dependency is on that maximum flow problem, and that actually has a with high probability guarantee, not a deterministic guarantee. So if we could try to get that to quadratic time as well, that would be a great improvement for at least implementation side. In terms of the theory, it would also be helpful because there's a pretty large constant factor sort of implied with that nearly quadratic as opposed to quadratic. We also have possibly a better approximation factor. So for the weakly visible case, we do not have NP hardness, but we use a 2 approximation, or 1/2 approximation for a hidden set. And if we can get that to exact, that would be a pretty good improvement, because then we would just be depending on the window partition, so we'd have a 3 and a 4, or a 3 and a 1/4. Can we extend this to polygons with holes? And the truth is that for hidden set, we have hardness n to the 1 minus epsilon hardness, whereas the log approx actually works for convex cover and with holes. So in terms of using them against each other, it's very unlikely that it would work for developing any kind of better approximation, because then that would actually imply that P equals NP, because then you would be able to approximate that number of that hidden set number with the log approx from Eidenbenz and Widmeyer. So in terms of polygons with holes, it's very unlikely that we could use hidden set and convex cover against each other like we did here. Can we deal with higher dimensions? So in this context, we've dealt with polygons, but could we possibly do convex polyhedra for covering general genus 0, say, polyhedra? Hidden set stays exactly the same, just finding this hidden set of points inside of this domain. Is it possible? And then another interesting idea is that looking at convex pieces where the vertices have to be polygon vertices, so no Steiner points. We use Steiner points for our triangles, so and also in our window partition. So could we possibly extend this? And I think this is the most realistic of our current open problems. Could we extend this to the case where the vertices of the polygon are all we can use for the convex pieces? And so here are the references that we used. And thank you for listening. And so this is for the in-person talk. We'll be asking for any questions at this time. So for the YouTube audience, if you have any questions, feel free to leave them in the comments, and I'll try to get back as soon as I can. Alrighty, thank you so much.